In this chapter, we will talk about three different bonding theories: valence bond theory, hybridization, and molecular orbital theory. VSEPR theory gives us a great way to predict the shapes of molecules, which can be verified by experimentation. It does not, however, tell us why bonds form. The basic theory about why bonds form is called valence bond theory. According to valence bond theory, a covalent bond is able to form when two half-filled orbitals overlap. Remember that each orbital can hold up to 2 electrons, so a half-filled orbital is one which contains a single electron. One atom has one of the electrons that will be part of the bond, and the other atom has the other electron that will be part of the bond. These orbitals have to overlap in three-dimensional space so that a sharing of electrons can occur. The larger the overlap area, the stronger the bond. Two p orbitals overlapping end to end are going to have more overlap and a stronger bond than two p orbitals overlapping at an angle. A covalent bond is able to form because the electrons in the bond are attracted to the nucleus of the other atom, in addition to being attracted to their own nucleus. A bond will form when the distance is optimal, the distance which yields the lowest potential energy. When atoms are too far apart, they don't have attraction for each other's nuclei, and a bond does not form. When atoms are too close together, there is too much electron-electron repulsion between one atom and another. At just the right distance, there will be optimal attraction for each other's nuclei and minimal electron-electron repulsions. We can look at orbital diagrams of the elements to see if they will be able to participate in bonding. Remember, the atom must have a singly occupied orbital, one with just one electron in it. For example, fluorine's orbital diagram shows an unpaired electron that could participate in a bond. Neon, however, has all of its electrons paired, so it cannot participate in bonding. There are two types of bonds, sigma bonds and pi bonds. The difference is in the way that the orbitals overlap. Sigma bonds have overlap along the internuclear axis. Inter means between, so the internuclear axis is an imaginary line connecting the nuclei of the two atoms. It is an end-to-end overlap, which can involve an s orbital and/or one lobe of a p orbital. Figure A shows a sigma bond formed with two s orbitals. Figure B shows a sigma bond formed with an s orbital and one lobe of a p orbital. Figure C shows the sigma bond between one lobe of a p orbital and one lobe of another p orbital. Pi bonds form by side-by-side overlap on opposite sides of the internuclear axis. A lobe from one p orbital can overlap with a lobe from another p orbital on one side. The other lobe of each overlaps on the other side. Electrons cannot be found in the middle of a p orbital where the nucleus is, so pi bonds do not have any electrons along the internuclear axis. Electrons in a pi bond can be found anywhere in either of the overlapping areas, and the whole thing is one bond. In order to have side-to-side overlap, the orbitals must be pointing in the same direction, parallel to each other. A py orbital from one atom could overlap to make a pi bond with a py orbital from another atom. However, a py from one atom could not overlap with a pz from another atom. The naming of the axes is somewhat arbitrary, but some scientists label the orbital that is along the internuclear axis pz. If so, a pz can overlap end-to-end with a pz to make a sigma bond. A px can overlap with a px to make a pi bond. A py can overlap with a py to form a pi bond. A single bond is made up of one sigma bond. A double bond is made up of one sigma and one pi. A triple bond is made up of one sigma and two pi. You can think of the first line in each bond as being sigma and each subsequent line is pi. For example, the single bond in hydrochloric acid is just a sigma bond. The double bond in the oxygen molecule is a sigma and a pi. The triple bond in the nitrogen molecule is 1 sigma and 2 pi bonds. We will talk about sigma and pi bonds more later in the chapter.